Hello, everybody. Welcome to the arguably more exciting part of the two-part module where we actually start to build the C++ extensions. As a reminder, a lot of this information is also within the CompuCell3D developer manual. And I have links to the idea sharing documents and the workshop Slack. This workshop is live streamed, recorded, and distributed on YouTube. I also want to thank the funding sources. So I asked very briefly for those of you maybe trickling in, if you were able to get your CompuCell compiled, great. If you weren't, as long as you have the Git repo cloned and you have a version of CompuCell on your computer, you can at least partially follow along, although you just won't be able to compile what we will be writing. So there's a distinction that we have to, yes, this one, the second part will be more of a live demo, so I will be making and writing these myself and showing it to you. So the first kind of question that we have to answer is, what is a steppable in a plugin, and what can we do with the plugin itself? So steppables, you all should be generally familiar with. Steppables are simply the module that the simulator calls after every MCS. The only difference between these steppables and the steppables you were using before is these steppables are at the C++ level, and therefore you can expect a little bit faster or a lot of it faster, depending on how many times this module is called, execution of your code. This is at the trade-off of not being able to write in Python and having to make your code into C++. The other option that you have are doing plugins. So plugins can have a steppable component, but they can also have two other components, a lattice monitor or an energy function. Lattice monitors are just modules that are called each time your CompuCell3D functions. For example, Metropolis fast. And when that makes a change to the cell lattice, i.e. accepts a flip attempt, the lattice monitor will act. As a side note, because this hasn't been covered before in the workshop, Metropolis fast is simply one of the iterators that CompuCell3D uses to calculate and attempt the flip pixel probabilities, pixel flip attempts. So it is just the iterator that goes through the voxels, picks a neighbor dependent on your defined neighbor order, and then calculates the energy differential and therefore the probability. So your energy function is slightly different than lattice monitors. The energy function functions at a similar timescale. It functions along with Metropolis fast, but this module is called with every pixel copy attempt because when you're evaluating the POTS algorithm, you have to determine your energy. And simply what these energy functions do is it just adds an energy term to the end of the previously computed energy. So you can simply think it's just delta E equals plus your new delta E for your new for the contribution of this plugin. Right, so the energy function allows a great way to extend if you want to have some sort of energy penalty or energy contribution from a secondary source that isn't necessarily handled by the existing plugins. To generally summarize, steppables allow you to, depending on your code, solve your system much faster. And plugins allow you to extend or evaluate in a different way, your Metropolis fast function, or from the base level, how CompuCell3D evaluates these pixel flip attempts. So there are some Twedit functionalities for setting up a plugin. So we can go to our Twedit window, and then we can say CC3D, CC3D C++, specifically, generate new module. We can click on that, and then we get this pop-up, which I have right here. So this puppet has a few options. You can, unsurprisingly, you can name the module. You select the director of their module. This is rather important. We'll discuss this in a second. We have not set up developer zone, so we keep main code layout. We need to determine whether it's a plugin or steppable. And then at the bottom are plugins specific functionalities. If you select Steppables, these disappear, right? So generally, where to target, if you're creating a Steppable, you can directly target the Steppable folder in CompuCell, and I can show you kind of pathing to it. So if I start from the base, right, CompuCell3D, okay. Or again, give it a second. Okay. From your base, you can do CompuCell3D, CompuCell3D Core, CompuCell3D Steppables. And this is where generally all the Steppables are held with CompuCell. Let's try this again. Okay, it's letting me open folders again. So you can do CompuCell3D, Core, CompuCell3D, and then you can see plugins and Steppables. So if you just want to kind of have this pre-constructed, I can just say, okay, we're making a Steppable, and then here's the file path that we would want to put in module directory. Okay. So let's make a Steppable. So let's walk through this. We do generate new module, module name. This can be whatever you want. On the slide, we have GrowthSteppables. On the one that I pre-generated, I named it GrowthStep. This just says what we have to reference when we call for this module from XML. And then we can select our target. I already have it selected to the correct location, our Steppables folder, because we are going to create a Steppable. We select Steppable, and as you can see, those bottom options disappear, and we want to keep Python wrap. Okay. And when you hit OK, you will get 10 files opening up in your Twedit. These are basically automatically making the CMake linkers along with some of the C code, with a couple of them having some sample code within them. And we'll talk about that later. All right. So as I said, it will create these 10 files. And this will come up later when we actually try to build this. You may need to manually add one of these linkers. I had to do that. I do not know if that's a me-specific issue or a general issue. So we can now first go to our project. So for me, I created GrowthStep as a module, so that'll start to show up. If you don't see it showing up, you basically need to run builds, and then it'll tell you the solution is updated. You tell it to reload, and then you should have your module show up as whatever name you gave it, shared. Okay. And to get it to compile, it's the same thing as before. We can either do all builds, or if you want it to be ever so slightly faster, you can go to GrowthStep shared itself, right click on that, project only, and then build only GrowthStep shared. So I can do that, and you can see I've already built it, so it is up to date. Once that's complete, we can then do the same as before and run install. And I will pause here for a moment for those of you who want to basically just create the template code and then make sure that it compiles. We have not done anything exciting with it. We are just making sure that you can create this create it. So let me go a step further. Plug in, just leave it empty, and then name it GrowthStep. And that should make sure it's initialized on this. So the simulation I showed you in the first half should just run. It's going to look exactly the same at this point, or it's going to crash. Okay. Give me a second. The windows, you have to remember you cannot have this open when you push stuff to it. Let's rebuild. Open. It's likely getting a crash because it doesn't understand the XML input. Let's go see the project, open recent project, and then simple simulation. Check that was edited. Nope, so it's trying to call GrowthStep. Does not. Let's make sure it is this issue. Okay. The XML linker didn't quite create right for me. Okay, we can talk about that in a little bit, but let's keep moving. It does compile okay. There was a slight linker issue that I have accidentally made. Okay, so as a reminder, if when you try to build the simulation, if you see a whole bunch of linker errors, it'll be something like LNK 201 you need to manually add CC3D GrowthStep to the Pi interface, right? If anyone is having this issue, let me know, and I can paste the exact path in the chat. Right, so I had to go into this CMake list.txt and then add a line CC3D GrowthStep that was not automatically generated. How many people are attempting to do this currently? Yes. Call it. Teacher. That fixes on. Nope, that will not, because I left values in. Okay. Hopefully when we move further, I'll incidentally fill in what's creating the linker error. Because we will be talking about the XML, filling out that XML field. Okay, so some things that you can do with the files. You can define how the XML is referenced with the proxy file. So we can go and check that really quick. Let me here. You can see our GrowthStep. We have our GrowthStep proxy. I'm going to open it in Visual Studio. You can see the proxy that it sees is GrowthStep. So you can name this proxy as you see fit. In the example I've shown here, it is using GrowthSteppable, whereas in my example, it is just GrowthStep. It is as you decide. For now, we'll just keep the name as is, as what we set the original name. Right? As stated, CMake lists will automatically update to include your new stoppable, apparently, or include your new steppable. There will be a few that are created when you make the original Twedit call. But the important files on when you're actually executing are your CPP and .h files, which is your header files and your CompuCell file, or sorry, C++ file. Right, so when we look at what's inside the CPP .pp file of our GrowthSteppable, you should see something very familiar. Well, sorry, this is the header file. We should see something very familiar, right? We have our defined start function, our defined step function, and our finish function. This is exactly similar to what we see in the Python level, with a special note that the C++ steppables are called before your Python steppables. So if you're concerned with the order of evaluation, C++ steppables will be evaluated before your Python steppables. So now we can start to say, start to look at the C++ file. So we will look at the auto-generated GrowthStep. So you can see here, here's my header file that has been filled with data automatically for linkers. Here's our step, our GrowthStep CPP file. And then we can go down here and then look at our start, our step, and our update, update, and then there is not a finish, but that is okay. We are not using that. So in our start function, we see it is empty, but our step function, it does pre-generate with a very simple code block. Basically, what this code block is doing is it's going through our cell inventory pointers, looking at each cell, and then extracting the cell ID and cell volume, and just posting it, and just writing it to console. Right. So this for loop iterates over the inventory of cells using our cell inventory pointer, a pointer to cell inventory, to print cell ID and cell volume. So a little bit more in depth is just the class object. The class for this object, cell inventory, is defined in this header file, and the implementation is in this CPP file. Internally, we are using STL, Standard Template Library, C++ maps to keep track of these cells. This statement, cell inventory to pointer cell inventory begin, turns an iterator to cell inventory. So we're looking at cell inventory as a standard map, cell inventory cell G, which is just your object. If you ever get somewhat confused in an IDE environment, you can always try to peek a definition if you're trying to see exactly what what something is attempting to do or where it links out. There is also, next, there's also a few helpful shortcuts in the Twedit menu. For instance, if you want to visit all the pixel neighbors, you can go to CC3D C++, visit pixel neighbors, and it will generate a block that visits all the pixel neighbors up to your neighbor order. And basically what this example block does is it will iterate up to your neighbor order and then tell you what the cell neighbors are. This is basically saying if not end cell, basically if I'm not that cell in that point, then report the cell ID. So similar to where you guys have done it before, just C++, visit all cells. There's also XML utilities and some attributes. And if you want to include field 3D automaton, in all of those. The biggest use is probably getting some of these visit functions. Right. So now that we're somewhat familiar with some of the functionality, it's important to remember when you're working on your own Steppable or plugin, it is okay to hard code values at first before worrying about encoding all of the capabilities of CompuCell like 3D, swig linkers, XML, or mesh types. The issue with not doing swig or XML is then you really can't link out to a user accessible area. So in order to change these values, you need to recompile the whole of CompuCell as opposed to just changing a value on the XML, for instance. Right? But if you're more concerned with making sure, say, your Steppable is doing something, then you are perfectly okay to do first pass hard coding. You do not need to get it perfect on the first try. So for our first exercise, we're going to try to actually create a GrowthSteppable, which is exactly the same, exactly what you think. It's just as the system iterates, we're going to add a certain amount to the target volume to allow these cells to grow as the simulation progresses. Right? So we want to go to our GrowthSteppable, C++. We have an empty start function at this point. And since we will not be defining these values in the XML, we will define them here. So I'm going to change to this block. And if you want, I can post this block in the chat. So if you want to just copy and paste it in your code, you're perfectly able to, right? So I can just take this, go to here, and then insert this. So what this is doing, similar to before, you're creating a cell inventory pointer, iterating through all the cell inventories, and then at every single cell, you're just assigning a target volume and a lambda volume. This is because by default, when you create a cell, it's just going to scatter and become dust. Right? So let me post this block in chat. So this is what goes in the start function. It's very simple. You're just going through each cell inventory and you're giving it a target volume and lambda volume. And why are we doing that? That is so when we move to our step function, we can have our step function modify our target volume to increase along a rate. Right? So now we can start to talk about that. What we are doing here is defining some float, which is our growth rate, and then saying we are going to go through all of our cell inventories again, and then we are just adding that growth rate to target volume at every step. So let's put that in step function. We will replace the example code because we want something more functional, albeit hard-coded. right? So I'm gonna do that. I will post this in chat. So this goes inside your step function. Now we have told our C++ code what we want to actually do with all of the cells in the simulation. So now we can try to actually install it. Since we only modified our GrowthStep CVP, we don't need to do all build. We can actually do, we can actually go to GrowthStep shared, project only, build only. So it'll build that. And then we can build the install. Now, assuming this is the default plugin definition, this is the alias, this should work. Without crashing. So if it's crashing, that just means it doesn't like the XML syntax. Okay. So has everyone been able to follow along to this point, if you're following along? As a reminder, even if you can't compile, you can still create these CPP files and kind of write along with, although you won't be able to actually compile. Here. Right, so this is a very simple type of code where we will just be modifying growth rate by target volume. I'll ask if Maciek is currently back.
Yep, I'm here.
So I have a slight issue.
Okay.
This is probably related to kind of the other thing where the linkers are broken. I'm trying to call just so that it'll load this hard-coded GrowthSteppable. And it is crashing like it's an
Because
XML
it should
dev
be
issue.
steppable. It should be called steppable. Steppable and type.
Okay. Okay.
And
It's
you
okay
have
to
to,
make silly errors.
yeah, ideally move it to steppable section, move it towards the end, like after
Yes.
apply.
Yes. Okay. Thank you. Sometimes you make silly errors and it's okay. This is
And
a habit for me
type.
because I've only written plugins.
And Michael, line 50, it has to be steppable type equals.
Thank you.
Yeah. And yeah, I think it should work.
Okay, so this should work.
Save it. Yeah.
Yeah, it's already saved. Okay, so we can run our simple simulation. Yeah, there you go.
Is it doing what it's supposed to do?
It should grow. It does look a lot more dusty than it necessarily should.
Yeah. You can always put print statements inside the loop, right?
Yes, so we will check
file.
that. Let's make sure. So we're gonna go
Oh,
through.
wait. So here you're iterating over the all cells in start function. So this function will get called once at the beginning. If you
Yes.
want to, oh, and you
Mm,
have it here, growth rate, right?
yes.
Yeah. So cell equals, hold on, let me just take a look at this. Growth rate. Yeah, it looks fine to me.
Make sure it's in there. You can check against. Let's do can open. Well, can I just force it to generate that there? No. Okay. Okay. Seems okay. Unless this is the call. This is messing it up. Okay. Let's let it run for a little bit. Maybe it's just noisy, but it should grow and fill the domain up. So we are assigning these volume constraints. This is a question for Maciek. Do I have to call volume plugin?
Yes.
There we go.
Yeah.
That is what was missing. Okay.
Yeah, so the only plugin that's loaded by default is VolumeTracker. And you need VolumeTracker because, when cell volume reaches 0, the cell is removed automatically. So we need this plugin to tell CompuCell when to remove cell. All other plugins like volume constraint have
There
to
we
be.
go.
Yep.
All right.
There you go. Yeah, your code is working.
So there you go. So we have now allowed a C++ code to directly modify the simulation, so all cells will grow at a certain rate. So to generate this simple simulation file, it's actually extremely easy. We can just use wizard. We can do new project. I'm not going to actually generate it, so I'm not going to give it a name. We can do rectangular slab. We're going to create cell A, cell B. The names of those are not very important. We will not have chemical fields at this point. And then you want to use one of these volume plugins so it actually knows to track. So volume flex, for instance, to make sure that it creates this plugin. And then it will, you don't even need to change the default size of uniform initializer. This is the pre-generated size that I had. And it will create this simulation. Right. So that's great. We have a simulation, it grows, but now we're hitting the issue of the fact that it's hard-coded. But before we move past that, let's extend the Steppable slightly. So now we're going to increase the target volume of the cells, but only for the first 100 MCS and only if the cell type is 1. So what do I mean by cell type is 1? We can pull up this, and then you can see each cell has a type ID. So it's going to look for this type ID, right? So let me do this. We can just simply replace our step function. And I will paste this code, right? then we will talk through exactly what this code is doing. So here's the code block I just put into my step function. So what we are doing here is now when we do step, if our current step is greater than 100, we return, meaning we just exit our GrowthStep step. Otherwise, we'll proceed through, similar to before. We're going to apply our one growth rate. We're going to go through all the inventory pointers. And then we're going to check to see what is our cell type. If our type is equal to 1, then we apply our target volume growth rate, right? So still relatively simple, not extremely complex, but we are building up functionality. So let's now go to our GrowthStep shared. We can then do project only, build only, so that our GrowthStep is updated. We make sure that we don't have this open. And then we can install. Now, if we reopen our simple simulation, should see a slightly different behavior. Yeah. So we can see only our cell type A grows while B just maintains its original shape. And we can see after a certain amount of MCS, which we know is 100 because we defined it, the growth stops. So I want to pause really quick here to make a point on the reason why I am going through a steppable slowly is not only because you could make your code faster by utilizing the C++ steppable, is that the linkers and the steppable are effectively the same between that and the plugin. So learning how to create these references in the plugin, this knowledge extends to the plugins, while being in a slightly simpler context, right? So now we want to move away from our hard-coded components, right? So say we want to aim to have an XML definition that looks like this, right? Where we've defined our growth rate. We need to modify a few things. The first thing that we will change is our update function in the CPP file. Okay. So I'm going to actually grab this whole block so that there's context in the chat and paste it so it's a little easier to follow along. And then we will go here, find our update function, and I will just replace the whole block. And then make sure it is still closed. Okay. This is upset because I have a slightly different name, so I need to update it to GrowthStep. Now you'll see one thing immediately that the IDE picks out is that growth rate is not defined. We will show that here right now, right? Before that, let's talk about what it does, and then we can talk about how to make sure your C file knows what growth rate is, right? So what we're doing here is we're looking at our XML element, growth, looking at the data, getting our first element, growth rate, right? And then we say, if this element exists, we assign this value, which we're retrieving with getDouble, basically meaning we're grabbing the value between that and returning it as a double, and then assigning it to growth rate. And that is all this block is doing, is just reading the XML, looking for growth rate, finding the first element, and then assigning it to some term. Right? So to define growth rate, it's relatively easy. You just want to create a double growth rate as a public class in the header file, right? So go here, go to public, and we'll just put it right under here, double growth rate. So all that needs to do is match. You can save that, and you'll see the squiggly will go away because it is now created successfully in the header file. Right. So finally, to actually get rid of the hard-coded element, we need to make a reference to this this created value, right? So where previously we had our step function where we had a hard-coded growth rate, we are now going to substitute this hard-coded growth rate with the pointer, right? So we're going to get rid of this, and then we're going to go this, and then right, you can see it's suggested. I might have misspelled it. Yes, okay. It is cases matter. All right, you can see that. I'll double check on this slide to make sure it's correct. Yep, you can see this pointer to growth rate. Okay. We can save this. I'm going to update the XML element to have to look like as we defined it previously, right? So we just want to have some growth rate tag. Get some separation just to make it look a little cleaner. And then we should be able to, after we compile, save and run. We should see the same response. We should see the same response. Okay, so let's go here, similar to before, project only, build only. It's going to create it. We can then install, which just pushes our changes to our Python. Right. Second. And while this is going on, I would like to pause here to just generally ask for questions from those of you here. I may have gone a little fast through the previous sections. So if there's somewhere you got lost or you want a better explanation, please ask me in chat so I can go back and cover that. that has gone. Now try to open this in player with our new growth rate definition. And we should see the same result. It grows for a little bit and then stops. Right, so that's how you make a very simple XML definition for a growth rate steppable. Do I have any questions from those of you here on anything from the start of this module till now that you would like clarification in? Or do you want me to go back and then show some of the steps in creating the code? Does the documentation show how to refer to every cell property? I don't actually know the answer to that. I might push that to mod check. I normally can try to check every property. Well, for an object, I'll do kind of the definition peak. That won't necessarily tell you what each one is. So, right, you can say.
So the answer to this is you should look at the source code. So in pods3d slash, there is this file called cellg.h. Yeah, there you go.
Yep. Yeah. So this is so normally when I get questions like that, I use the IDE to peek the definition, right?
Yeah.
So these are all CellG classes. Then we can see for this CellG class what the available properties on it. Does that answer your question, Troy? Or is there something more specific? Okay, cool. So it's a good question. Okay. So let's move forward a little bit and let's try to get a slightly different definition where we try to say, what if we want growth rates for different cells? Right. So if you wanted to ask, if you want to do allow different growth rates for different cell types, we need to move away from using our previous definition in the header file for just a double, or sorry, for a double growth rate, because now there is not only one growth rate, you have a growth rate for every single cell type, which is why we will create a map, right? So we just can simply substitute what we had as previously double growth rate to standard map unsigned int double growth rate map. It's basically is a mapping to tell you what are my growth rates for each cell type. Okay. So now we can say, okay, I want my XML definition to now look like this. Let me make this slightly bigger so it's a little easier for all of you to see. Right? I want now call the steppable type, GrowthRate, have cell type 1 and 2, which have their own individual growth rates, right? So outside of defining the map for the growth rate map, what else do we need to do? We need to again go to our update function and then create a list of these XML elements, go through this this growth vec, get our attributes, right? So look for cell type, get attribute as unsigned integer, and get our value itself as a double, right? So then we create our cell type, growth rate temp, and then we assign it to our growth rate map, right? We use this temp value to create this growth rate map, right? And then we assign cell type to the index in the growth rate map and the value to that index in the growth rate map, right? So let's put this in our update function, replacing what we had before. Right? So previously we just said, let's pull our element and then assign that it's double. So we now create the list, and then we're now creating a map for cell type as our output, right? So this is now our pointer. Okay. This by itself isn't too much useful. So we now can modify the step function, right? So we need to make a map iterator, right? So that's all we're doing in this, just map unsigned in double iterator map iterator, right? So we need to put that first at the top. And I'll post all this code in the chat here in a second. So it should be at this level. You need to let it know that it needs to make this map iterator, right? And then we change the way we're going through, right? So that we're now doing the map iterator to check versus our growth rate map. I'll try to explain this in a coherent manner for those of you who have not dealt with some of these functions and why they exist like this, right? So changing this, so we're creating our map iterator. And what we're doing is we're saying map iterator is equal to the pointer growth rate map find unsigned int cell type, right? So we're finding the value of cell type on the growth rate map while iterating through all the cell inventories, right? So we're checking what these cell types are while going through the inventories. We're saying map iterator, and then we say if we're not at the end of the growth rate map, then we take the second value, or sorry, we then assign the map iterator second, which is our value itself, right? To add to the target volume. To try to show that a little bit better. So when you create this map iterator, when you create the mapping, it's going to create something like this, where in this case, this wouldn't be A, this would just be 1, or, right, that's our cell type, and then some value, right? So when we're going through the map iterator, it's going to see our A, and then our 12. So our map iterator first component is the key of the map, and the map iterator, the second, is the value. So going back to here, that's why we retrieve the second value of the map iterator, right? We're basically saying, let's go through, for our cell type, we check to make sure, does this cell type have a value on the map iterator? If it does, we assign that value to increase the target volume. If you're confused, I don't exactly blame you. It's not the most intuitive, at least for me. I'm sure it's intuitive for others. It is not the most intuitive. Right? So now we can do this sort of function. And now if we take the Steppable and then say, let's go here and replace our Steppable definition with our new definition, this should function correctly. After I do as I've shown before, I need to go to GrowthRate step shared, build. Well, I'm supposed to do project only build. Let's do project only, build only. Okay, did that, and then I'm gonna try to install it. Give it a second here, as it generates the linkers. And we'll know that this works not only from the result, but by the fact that it will throw an XML error or not. You wanted to add new properties to the cell. Can you do it from there? As in to the cell G object? If you wanted to do that, I think one of the ways you can do that is just use the extra members group with the extra attribute pointers. Although the exact way you would do that currently is escaping me. Okay, so this has finished. But let's make sure this works. So now we have an XML definition with cell type specific. This is an easy fix because I'm using GrowthStep and not GrowthSteppable. Right. So you can see here for the first 100 MCS, we have the cells grow at different rates. So I think we assign B to be a higher rate so you can see it grew faster. And that is in fact what we defined. This is a simple way to create these XML rate mappings. Okay. For time, I'm not going to go over the VolumeTracker, which is a lattice monitor. Though the lattice monitor is available from this link. So that is the example for how to do this lattice monitor. All this VolumeTracker basically does is it says at every flip attempt, did the cell gain a pixel? Did it lose a pixel? And then it reports it into your terminal, which you can see it is currently spamming my terminal because I left this running. Okay. So instead, we're going to be using our last bit of time into looking at an energy function, which is one of the more exciting ways you can extend CompuCell. So as a reminder, the way that we do it, so we're going to just apply a simple energy penalty to our flip attempt, basically. Okay. So these energy function plugins work by giving a hook to modify the cell pixel copy attempt probabilities. As a reminder, we basically do a Boltzmann probability. So the full form is here, delta H, you have likely seen as delta E before. It is just the change in energy between the states. By default, your K and your delta are 0, right? So delta is 0, K is 1. So that's why you've normally just seen it as delta E over T, because effectively, unless you decide to define these, that is the values you are using. So this energy plugin allows us to modify delta H such that we add a defined energy to delta H itself. This is how all the energy plugins function, right? I guess there's a special note of that in cases of delta H equals 0, the probability becomes 1/2, as opposed to just taking the resultant of this probability function. Okay, that's a duplicate slide. So the focus when creating this plugin will be on this function called changeEnergy. So what changeEnergy does is it looks at the current and the target pixel locations, matching to previously used terminology as you'll see them. New cell is the target pixel, i.e. the pixel getting flipped. Old cell is the source pixel, the pixel being copied, right? So these are the two separate pixels. It checks what's currently in them. It grabs whatever inventories you want, calculates the delta H contribution of whatever you're concerned with, and then it's added to the end of the energy functional. So this means that every single flip pixel probability attempt at every single pixel flip probability attempt, it adds the resultant of this delta H between new cell and old cell. Right, so for a simple energy penalty plugin, in the very bare bones hard-coded, we can try to create a model that checks the target pixel field concentration and then apply an energy penalty based on that value. So for this case that we're thinking of, it's basically going to only check new cell to see what is the concentration of the field in this pixel that I'm trying to flip to, and then it will add a corresponding energy penalty to accepting that pixel flip attempt. From a high level, you can consider this as sort of an impedance into moving into an area that the cells do not like. So if there is way too much. So in this case, it's just going to be increasing. So basically, if there's too much of some field like ECM or just particulate, it's just going to make it harder to move through that space. So a similar but different plugin would be chemotaxis, which would check the field concentration between new cell and old cell, between the target and the source pixels. This one is only going to check against the target, right? So first, I'll show you kind of a completed code in it with XML linking that uses a slightly more complex energy functional, but it's still a Hill function. It's just a combination of Hill functions. And then I'll show you what that ends up looking like. And then we can briefly attempt to create a simple hard-coded version, which the highlighted should be sufficient in creating. So for me, I have this simple energy plugin. So let's take a look at our changeEnergy, right? So this is what actually tries to apply this energy, right? So we initialize it as 0. We say if new cell, and when you automatically generate this, it'll make kind of these itself, right? So if new cell, if I'm looking at the pixel I'm attempting to flip, I will look over this. So what this is it's just looking over a parameter map, right? So for this, I have a definition where the first field is the cell type. The second is the energy penalty maximum you want to apply. And then the third is the power of the Hill function, right? So similar before, we do the map iterator, parameter maps, find new cell type. We're going to find what cell is currently, we're going to look at the new cell, the new pixel we're trying to flip. And then we're going to find the power value, which is map iterator second power, and the lambda value, which is our maximum. So for this one, it is our maximum times our first Hill function times minus our second Hill function. Sorry, it's the maximum times brackets across both, a inverted Hill function and a positive Hill function. The idea behind this is that it creates kind of this nominal density that the cell will want to see. Right, so now we can add this energy. So this is just an else case, so that if I define a special case, it doesn't do the combination. So we don't need to worry about that, right? But what's basically happening is we're adding this energy penalty at each step. So I have it here. So if we run this, right? So this is a simulation to kind of show this idea. It's some field which I've called ECM. It has a region at 1 concentration. It has a region at 0 concentration. It has a region at 10. All of these values are locked. And then I've assigned two cell types, right? That you can see in green and blue. Only the green cells care about this field density, right? So if we look at the solution as it moves across, you can see that the two cell type A's will hit the edge of this ECM and not want to move into that space. They'll just get stuck on it as if they've hit a solid wall, while the center cell will just walk on through, and the cell that doesn't care about the field will also walk through. So this is one of the interesting things that you can get away with by modifying this energy functional in a way very particular to your problem. Right. So kind of show you this is, right? So I do similar to before, just plug in, right? Looks like all the other plugins. You can define it as such and then say what the cell types are. Okay. So you can try to make a hard-coded version of it really quickly. The keyword is try, but it will kind of show you what the generated plugin code will look like. So we're going to call this just simple E, very simple. We're going to target the plugin folder because we are now using a plugin, right? You want the code layout to be main code because we're not using developer code. We're using a plugin, and then we want to select energy function, right? Because we're only going to modify this delta E value. I think I do have to come back here really quickly and clarify something that I got wrong. New cell, old cell. New cell is the cell attempting to flip. And I think I got this backwards on accident. New cell is the cell that's attempting to flip and overwrite. And then old cell is the one that is getting copied over. I want to clarify that very quickly, right? So you're only looking at the target pixel. Source pixel, right? So to make it much more clear, right? So let's do this. I'll have to clean up the CMakes later for this, but that's okay. So we're gonna create the plugin, and you can see similar to before, it's going to open a whole bunch of files. But the thing we're most concerned with is our simple E plugin .cpp and simple E plugin.h file, which is our header file. Okay. So when your plugin is created, you're gonna see some different functions. It's going to initialize. You have an extra in it, which we may have to use. And then you can see our changeEnergy, right? So it'll do if old cell, else, if old cell, if new cell, else. Right? And for our reason, our problem, you're just using if new cell. And then we're going to add some amount of energy, right? the first thing we need to do is we need to go to our header file, and then we need to make a public variable field3D float concentration field. The start is particular. This is just something that is defined in the C++ code. And then we can go to this and say, we're going to attempt to get our concentration field, which we just called by a name. And this one, it was very specifically ECM. So I'm just going to hard code that in right there. And then we get the concentration of the field at that point. And then we apply the energy. And then we can see whether or not this actually compiles very quickly. Build. I need it to update the environment. It's gonna figure out that there's a new plugin here. And then tell me to refresh. Or it already refreshed while I was modifying the files. Okay. Let's reload. And actually, this will show one of the linker errors that I got earlier, so I can go over how to fix that. So we're going to build. This may take a bit. Okay, good. So this is one of the errors that I was talking about earlier, the LMK 2001. Also, somewhere I forgot a 70. Nope. There's a possibility I also messed up the closing of the brackets. No, because this isn't even the steppable. Okay. It is here. There. So 70, right? I forgot a semicolon. So the point that I made earlier, the CMakes, so it should create a linker here, but it doesn't for me. So I can go and manually add our simple, and that should fix our issue. Okay. Okay. I think we did fix the issue. I just have a bad bracket in the file itself. Syntax error 73. Okay. Yes. Yes, because I forgot to end line again. Okay. While this is building, I'm going to kind of make some final comments. If you do want to contribute a plugin or Steppable to the release of CompuCell3D, you are welcome to, but there is kind of a higher scrutiny to integrate it with the core code. So the short list is this code needs to be extensible, meaning it needs to have some form of error checking to let users know when and if it's the one messing up and how it's messing up. The method should work in all lattice types, i.e. square and hex lattices, adjust to all copy ranges comfortably, and work in 2 dimensions or 3 dimensions. You should have, if possible, a CC3D ML counterpart and be Python controllable. Documentation with clear explanation of purpose of the function and how it functions at the mathematical level. And then, of course, include some sort of demos for the method. So let's go here. And I apparently am very bad at suppressing outputs. Or okay. Yes. I'm just trying to write too fast. All right. So I'll try to find why I can't write this. Okay. Likely, I've made a very simple mistake when trying to write this code because it is not happy. So classes. But if anyone has any questions on how to do this or wants me to go back to previous sections, please let me know and we can do that very briefly. I believe after this is a short break. Hayden, correct me if I'm wrong.
Yeah, we'll come back at 3 o'clock.
Okay. Yeah, that's what I thought, that I was missing one of these. That's closed. That goes there. Yeah. It's closed. It's closed. It's closed. I'm missing one here. Let's see if this works. Mhm. Does anyone have any questions? I know this is kind of a lot. That built correctly. Let's see. Install it. That succeeded. We can go here. Let's take this ECM density plugin. We're gonna quickly just empty this out and then just call it simple E and then see if that works. Yep. I think so. Yeah. So you can see it's apply the energy penalty. So, okay. So it's, yeah, it's applying it in the direction such that it's preventing low ECM movement. You can see you can very simply, I accidentally wrote it on the wrong side of the energy functional, which is why it is here. So to fix that, what you can do is just change the sign. If you want it to go the other direction, and get stuck on the other side, you can just change the sign to be minus equals. Oh, yeah, because I had one minus. Good. So in terms of trying to get a very simple hard-coded plugin, you can do that relatively quickly. It's just not as extensible than as you add more complex XML functionality. You will start to get more complex looking files due to the use of these, in this case, a mapping, and in the case of the simple energy penalty, I think I use an unordered map. Yeah. But it to then start to assign these XML values, it starts to get a little bit more complex, but it's good to add kind of small bits of details at a time, as opposed to attempting right off the bat to do all or nothing. That is the end of the current plugin. I do current plugin module. I do really encourage everybody to attempt to do the volume tracker if you want, or at least go through the GrowthSteppable to get comfortable with how to make these XML linking, how to link the XML values to your code itself. So then you have an easier time modifying these values without having to compile repetitively.